Hypernetworks have gained significant attention in recent years due to their ability to improve the performance of various artificial intelligence (AI) models. By leveraging the concept of multiple inputs and outputs, hypernetworks can enhance the efficiency and accuracy of AI systems across different domains. In this article, we will delve into the inner workings of hypernetworks, explore their applications, and discuss the technical aspects that make them so powerful. A hypernetwork is essentially a neural network that generates another neural network's weights instead of producing output predictions directly. This allows the generated network to adapt to new data or tasks without requiring extensive retraining. The process involves feeding input data through the hypernetwork, which then produces a set of learnable parameters that define the architecture of the target network. These parameters can be used to fine-tune the target network for a specific task or dataset. Hypernetworks have numerous potential applications across various fields, including, but not limited to, 1. Neural architecture search. Hypernetworks can be employed to automate the search for optimal neural network architectures, leading to improved model performance and reduced computational costs. 2. Transfer learning. By generating a hypernetwork that captures the knowledge from a pre-trained model, it becomes possible to transfer that knowledge to other tasks or datasets with minimal additional training. 3. Few-shot learning. Hypernetworks can facilitate few-shot learning by generating networks that can adapt quickly to new classes or tasks with only a handful of examples. 4. Robotics and control systems. Hypernetworks can help optimize control policies for robots and other complex systems by generating networks that can adapt to changing environmental conditions. 5. Generative models. Hypernetworks can be utilized to generate diverse and coherent samples from generative models like generative adversarial networks, GANs, and variational autoencoders, Vs. Technical details. While hypernetworks offer exciting possibilities, there are some technical considerations to keep in mind when working with them. 1. Computational cost. Training a hypernetwork can be computationally expensive due to the need to train both the hypernetwork and the target network. However, techniques like gradient checkpointing and parallelization can help mitigate these costs. Overfitting. Hypernetworks can suffer from overfitting if the learned parameters become too complex, or if the training data is limited. Regularization techniques like dropout and weight decay can help prevent overfitting. 3. Optimization algorithms. Choosing the right optimization algorithm is crucial for training hypernetworks. Stochastic gradient descent, CFD, and its variants are popular choices due to their stability and convergence properties. Network architectures. Hypernetworks can be applied to various network architectures, such as convolutional neural networks, CNNs, recurrent neural networks, ARNNs, and transformer networks. Each architecture has unique characteristics that affect the performance of the resulting hypernetwork. Hypernetworks represent a promising area of research in the field of AI, offering novel ways to improve the efficiency and accuracy of various machine learning models. While there are still challenges to overcome, the potential applications of hypernetworks make them an exciting development worth exploring further. As more research emerges, we can expect to see even more innovative uses of hypernetworks in the future.